Here's another interesting substitution cipher. It's called a polyalphabetic substitution. So instead of using the same substitution every time, like every E goes to some other letter, which makes frequency analysis possible, we're going to do polyalphabetic. So sometimes things are encoded with different letters, but there's an order to it. I'm not 100% on how to pronounce this, but luckily Google does. So if I just type the word in here with the correct diacritical marks, and I select French, we don't actually want to translate this. All I'm going to do is have Google pronounce it for me. Vigenere. Vigenere. All right, pretty close. We need to start off with this square, a Vigenere square, if I'm saying that right, or even close. So what this is, it's the same shift ciphers that we've seen before. On the first one, there's a shift of 0, so it's not really a cipher, and then it goes here. The A starts here, so technically, in the way we were talking about this before, that'd be a shift of -1, then -2, then -3. But it's the alphabet in order, just starting in this rhythmic place where the A's just slide over one to the left each time, and the rest of the alphabet follows. So the way this works is you need a word or a phrase or a sentence as a key. Usually shorter keys are easier to remember, but less secure. That's always a trade-off. So suppose you want to encode the secret message, I love you, with the key of cat. So the way this works is the word cat is just repeated as many times as necessary. C-A-T, C-A-T, C-A. And then you do your ciphertext using this square. So let's draw on a grid. Now the first letter we need to encode is I using a C. So we go over here to the I that we want to encode. We read down to the C column, or the C row, and we get that that is going to be a K. The L, we come over here to L, we read down to the A row, that stays an L. Anything in the A row is the same, which is unfortunate. So then O, we encode on the T row, so you go to O and then go down to the T row, you get an H, it looks like. And then just proceed, the V you encode on the C row, and there's your message. KLHXERQA is what that is encoded as. And you notice here that there are two O's in the plain text message, but they go to different letters in the ciphertext, which is how you defeat frequency analysis. So to decode, just reverse the steps. Here's our plain text message, VKXWJAX, and we're going to decode with the key vote. So just repeat the key as many times as necessary, even if it ends up a partial word. You're going to decode the letter V using the key of V. So go to the V row and find a V that is right here, so that means it's plain text A. You're going to decode on key O the letter K, so go to the row O, scroll over till you find a K, that is in the W column. Similarly, in the T row, look for an X. Right here is an E. In the E row, look for a W. That makes it an S. In the V row, look for a J. You can probably tell what the message is going to be, but follow it through anyway. On the O row, look for an A. And on the T row, look for an X. But wait a minute, we already did the T row on an X. So the plain text message is awesome. But notice an interesting thing here is that X was encoded, or E was encoded as X both times because the key happened to be T. And that is how this is mathematically defeated. On a very short message, it's difficult, but on a longer message, the fact there is a regularity here. If your key is only 4 characters, you will get some repetition of the same 4 lines every single time. And that's how you can develop a mathematical method to decode this, even though it seems pretty impossible.